Okay, let us start off with exercise 20 again. We were unable to solve this in the previous video. So again we are in the ring of 2 by 2 integer matrices. Matrices with integer entries under, of course, matrix addition and multiplication. Now we have to find those matrices that have inverses under multiplication. So let us start like this. Let A, B, C, D be a matrix in our ring such that the determinant AD minus BC is either 1 or minus 1. If AD minus BC is equal to 1, we have D minus B minus CA belonging to M2 set such that now if one performs the multiplication of these two matrices, then what do we get? AD minus BC. Let's first write the entries and then we will decide what they ultimately will become. Minus AB plus BA is 0. CD minus DC 0, minus BC plus AD. Now because AD minus BC is 1, so this becomes the identity matrix, 2 by 2 identity matrix. And if we change the order, D minus B minus CA, A, B, C, D, then DA minus BC, BD minus BD, this one is 0, minus CA plus AC is 0, and minus BC plus AD. Again, this is the 2 by 2 identity matrix. So that means when the determinant is 1, this matrix plays the role of the multiplicative inverse of this. And note that this matrix again belongs to M2Z because originally A, B, C and D were integers. So these are also integers. So the matrix has integer entries. On the other hand, if the determinant is minus 1, then this matrix now belongs to, let me write it here, minus DBC minus A belongs to the ring such that minus dbc minus a times abcd minus ad plus bc minus bd plus bd is 0, ca minus ac is 0, cb minus ad. So ad minus bc is minus 1, so bc minus ad is 1. 1 0 0, this one is also 1, and similarly this will also be the 2 by 2 identity matrix. Minus ad plus bc, again ab minus ba 0, minus cd plus dc 0, cb minus ad. So when the determinant is minus 1, this matrix instead plays the role of the multiplicative inverse of our original matrix ABCD. So that means if we consider an integer 2 by 2 matrix whose determinant is either 1 or minus 1, then it has multiplicative inverse in the ring. Is the converse true? Is every matrix in M2Z that has multiplicative inverse like this, whether its determinant also has to be plus 1 or minus 1? Actually that's the case, and let's now show that. So once we show that, this will characterize all the matrices that have multiplicative inverses, or in other words, all the elements in this ring that are units. Okay. Next, let alpha, beta, gamma, delta be a matrix in the ring such that for some matrix epsilon, beta, theta belonging to M2Z, we have so now what we are assuming, we have assumed a matrix in our ring that has a multiplicative inverse, and that inverse is this. Then we can use only one of these equations, say the first one. Now we know from elementary matrix theory that the determinant of the product of two square matrices is equal to the product of their individual determinants. So using that, we can write alpha delta minus beta gamma. So the determinant of this left hand side will be equal to the determinant of this times the determinant of this. The determinant of the first one is this times the determinant of the second one minus theta is equal to the determinant of the identity matrix, which is 1. Now in this equation, note one thing, that because these are all integer matrices, alpha, beta, gamma, delta, epsilon, zeta, eta, theta, all these are integers. So these two are integers. Okay, so the product of these two integers is 1. So we are going to write like this: since alpha, beta, gamma, delta, epsilon, theta, these are integers, so are these two, alpha, delta minus beta, gamma, and epsilon, theta minus theta, eta. Hence, so what are the possibilities for these two integers? Either both of them are equal to 1 or both of them are equal to minus 1. These are the only two possibilities. We don't really care about this one, but this is either 1 or minus 1. Hence, this is equal to plus 1 or minus 1. This shows that the matrices in M2Z which have multiplicative inverses are those matrices which have determinants either 1 or minus 1. So these are the only matrices which will have multiplicative inverses. We can conclude like this. So the matrices in our ring that have multiplicative inverses are those with determinant 1 or minus 1. So this completes the solution. Now 21. Suppose that a number of rings are given, R1, R2, etc., Rn. These are rings that contain non-zero elements. That means each one of these rings has some non-zero element in it. None of them is the zero ring. Show that the direct sum has a unity, if and only if each of these rings, each Ri has a unity, a unit element, or in other words, a multiplicative identity. In this text, a multiplicative identity, or what we normally denote by 1, the symbol 1 in a ring, by definition is a non-zero element. However, in some texts, like in Topics in Algebra by Herstein, that restriction is not given. But here for us, in a ring, 1 is always not equal to 0. Okay, so we now have to prove two things. First, if each one of these Ri's has a unity, then this direct sum of them also has a unity and its converse. So let us prove the easy one first. First, assume that for each I between 1 and n, the ring Ri has a unity. We also denote it by this symbols there, 1 suffix Ri. Okay, it denotes the unity in the ring Ri. Then consider this element. This element is an element in the direct sum, and what is okay, now this element, besides being an element in this direct sum, is also a non-zero element. In fact, every component of this element, if we call these individual entries components, every component is a non-zero component, is a non-zero element in the corresponding Ri. Why? Because each one is a unity, so by definition each one is non-zero. Okay, so then this is a non-zero element of the direct sum such that for any element a1, a2 up to an belonging to we have these things. by the definition of multiplication, which is component wise in a direct sum. So this is again our original n tuple, and we have to also switch the order and show that that product also gives us the original element itself. See, we are not told about the commutativity of these rings, so we don't know whether this direct sum is a commutative ring or not. So not only do we have to show that this times this is equal to this, but we also have to show that this times this is also equal to this. So this is a unit element or unity in our direct sum. Conversely, assume that this has a unity, say B1. Now we don't know what the components are. Bn. So that is the unit element in this direct sum. Say the direct sum has a unit element like this. We now have to prove that each Ri has a unit element. Okay. Now note that the assumption that this is a unit element does not immediately tell us that each Bi is non-zero. It just says that this n tuple is not equal to the 0 tuple, all of whose entries are 0. That means at least one Bi is non-zero. Okay, so it only says that much. However, we can prove that each Bi is non-zero. Let us first do that. For each I lying between 1 and n, we choose an element Ci belonging to Ri minus 0. these choices can be made because it is given that each Ri is a ring which has at least one non-zero element. That means no Ri is the zero ring. There is something else besides zero in every Ri. So we can make such a choice. And there are finitely many Ri's, so such a choice can be made. Okay, then the fact that this is a unit element in this direct sum now gives us this. Okay, so we get this, and we are getting this from the assumption that this is a unit element. This implies Bi is equal to, no, not Bi, but Bi times Ci. Bi times Ci is equal to Ci for all I varying from 1 to n. Now, since the Ci's have been chosen to be non-zero, each one, so Bi cannot be 0, because if Bi is 0, the left hand side is 0, contradicting these choices. Since each Ci is non-zero, each Bi also has to be non-zero. Now for Ni, or let us take J lying between 1 and n, and any element Aj belonging to Rj, we have. Now our aim is to show, okay, we have shown that each Bi is non-zero. That means for this J, Bj is a non-zero element in Rj. Now our aim is to show that this Bj is actually a unity in Rj. So if we multiply any element in Rj by Bj in both the ways, that is Aj times Bj and Bj times Aj, both of them should give us Aj. That's what we want to show. And we can only use the fact that this is a unity in the direct sum. So now we have, using that fact, so since this J is any integer lying between 1 and n, so I am generally showing Aj somewhere here. Aj can be the first entry, Aj can be the last entry also. Bj, B, n. This is going to be equal to so in this element all the entries except the jth one are 0. The jth one is aj. Okay, so that's what this n tuple is, and this is equal to and in writing these two equations we have only used the fact that this is a unity in the direction, nothing else. But now what do we get from this? We don't care about the other entries, we only see the jth entry. The jth entry on the left hand side is going to be aj bj because component wise multiplication. Here the jth entry is aj and here the jth entry is bj aj. Thus this implies Bj is a unity in Rj. So Rj has a unity, and since j was chosen to be any element, any integer between 1 and n, so each Ri has a unity, so that is the converse, and this completes the solution. Then 22. Let R be a commutative ring with unity and U of R denote the set of units of R. Prove that UR is a group under the multiplication of R. And this group naturally is called the group of units of R. This group is called the group of units of R. So that means a commutative ring with a unit element is given to us, and in it we are considering this set which consists of all the units in R, that is those elements which have multiplicative inverses again in R. that we have to prove is a group under the multiplication in the ring. The first observation is that the unity of R itself is in UR. It is also an element that has a multiplicative inverse, and in this case the inverse is the element itself. Let 1 belonging to R be the unity in R. Okay, we are already writing the unity in R, so there is no need to write belonging to R. Let 1 be the unity in R. Then 1 belongs to UR. So that UR is a non-empty set okay. Now to show that UR is a group under the multiplication in the ring, we need to show the 4 axioms. That is, if we take 2 elements from UR, the first thing is that UR has to be a non-empty set, that we have shown. Then we need to show that the product of any 2 elements from UR is again in UR. Then multiplication is associative, which luckily is already there in the ring. Then there is an identity element. The role of that will be played by 1, and every element has an inverse. So let us start. Let U and V belong to U of R. Then there exist elements X and Y belonging to R such that Ux is equal to 1 and Vy is also equal to 1. Actually we should have written Ux equal to 1 equal to Xu. That is also part of the fact that U and V belong to UR, but we are not writing that because it's given that R is a commutative ring. So if Ux is 1, then Xu is also 1, and that's why we are also not writing Yv equal to 1. Then Xy belongs to R such that UVXY, using the fact that multiplication in R is associative as well as commutative, we can write this product as Ux times Vy. There are many intermediate steps. Okay, I am not showing those things. For example, you will first write like this: UV X and then Y. Here you have used associative law once, and then you use it again, and then use commutative law to change the order and such things. You know what we have done here. There are many intermediate steps, but they are routine and we are not writing those things. So this is 1 times 1, so that is equal to 1. And this also shows that xy uv is equal to 1. Since the ring is commutative, we are not mentioning those things. Hence, so what does this tell us? This tells us that xy is a multiplicative inverse of uv because their product is 1. So that means uv is also an element in the ring which has multiplicative inverse. Hence, uv belongs to ur. Since multiplication is associative in R. So it's also going to be associative if we restrict our attention to the subset UR. It is automatically associative in UR. The element one belonging to UR acts as an identity under or with respect to multiplication. In fact, this is true in the entire ring, but we need only UR, and in that also this continues to act as the identity with respect to multiplication. Now we need to prove that the inverse of U is itself again, U has an inverse in UR. Now note that under multiplication U has an inverse, that is the first thing, and that comes from the fact that U belongs to UR. In UR we have considered those elements that have multiplicative inverses, but now we want to say that that inverse itself also belongs to UR. Next, from the equations ux equal to 1 equal to xu, let's write xu for once. We are getting these equations from the fact that x is the inverse of u. But the same equations also tell us that u is the inverse of x, and in fact x is invertible. X has a multiplicative inverse which is u. We see that u is a multiplicative inverse of x, and hence x belongs to UR. So the inverse of u also belongs to UR. Thus UR is a group under the multiplication of R. And in fact, because it's given that R is commutative, this is an abelian group. So this completes the solution. We have to determine this group of units for the ring of Gaussian integers, that is complex numbers whose real and imaginary parts are both integers. Let A plus Bi belong to this group of units. Okay, but you understand A and B are integers. Then A plus Bi is a unit in this ring, so that means there is some other Gaussian integer C plus Di such that A plus Bi times C plus Di is the integer 1, which is the unity in the ring, of course. Then there exists C plus Di belonging to this. In fact, since we have already seen this fact that if U belongs to UR, then X also belongs to UR. So if you want, you can write C plus Di belonging to U of Z I, but there is no, we won't get anything new from writing that. So we just write C plus Di belonging to Z I such that equal to 1. This implies A square plus B square times C square plus D square is equal to the square of the absolute value of the complex number A plus Bi times this one, which we know from elementary properties of complex numbers, is this C plus, okay, let me write it in the next line. And this for us is 1. This is equal to 1. Okay. Now note that because these are Gaussian integers, so A, B, C and D, these are ordinary integers, and as such A square plus B square and C square plus D square are non-negative integers. Since So we must have what? And their product is 1. So both of them have to be equal to 1. Now the only other possibility that both of them are minus 1 in this case is not there, because they cannot be negative. Now we are given two integers a and b such that a square plus b square is 1. So this can happen in exactly 4 ways. Either you see both a square and b square are non-negative and both are integers. None of them can be greater than 1, because if say a square is greater than 1, then a square plus b square is also greater than 1. So how can that be equal to 1? So both of them must be less than or equal to 1. That means this as well as this. Combine this with the fact that a square and b square themselves are integers. So that means either a square is 0 or 1. Similarly, b square is either 0 or 1. If a square is 0, then from this equation we get b square equal to 1. So if this is the case, then b square is equal to 1, which gives us two possibilities. B is either plus 1 or minus 1. If a square is equal to 1, then b square is equal to 0, but in that case, since a square is 1, so a is either plus 1 or minus 1. And in these two cases, these are also included. So we see that from this equation, we get these 4 possibilities. Is either 1 comma 0 or minus 1 comma 0 or 0 comma 1 or 0 comma minus 1. Correspondingly, a plus bi is 1, or it will be 1 when a is 1 and b is 0. Similarly, for this choice, a plus bi is minus 1, or if a is 0 and b is 1, then a plus bi is I, and if a is 0 and b is minus 1, then a plus bi is minus I. So these are the 4 possibilities, and in these cases you can see that each one of them is a unit in the ring of Gaussian integers. Why? 1 is a unit because 1 is a unity. Minus 1 is a unit because minus 1 times minus 1 is 1. And I and minus I are units because each one is a multiplicative inverse of the other. And they are the only possible units. So, or in fact, because we are determining this group, we can write like this. So this is the group of units of the ring of Gaussian integers. Exercise 24. If these are commutative rings with unity, okay, each one has unity. So each one has unity. So from a previous exercise we know that their direct sum also has a unity. Show that, and the direct sum is also a commutative ring because each one is a commutative ring. The group of units of the direct sum is the direct sum of the group of units. Now you should understand that here there are two types of direct sums. Actually there is no, I should not say there is no difference, but there is a slight difference. The direct sum you see here is a direct sum of rings, but the direct sum you see in the on the right side is a direct sum of these groups. Okay. Generally we have the concept of direct product of groups, but direct product becomes direct sum when the groups are commutative, and in this case they are commutative because our rings are given to be commutative. So that means the multiplications in these rings are commutative, and these groups, each URI is a group under that multiplication. So each one is a commutative group, an abelian group. So that's the thing about this equation. Okay, let us now see the solution. So we will just have to show that each side is a subset of the other. So let us start by considering an element on the left side. So let this belong to but before before considering these things, I think it will be better if we write that notation for the units in the RIs. Let 1 RI be a unity in Ri for I varying from 1 to n. Now let this be any element in the group of units of the direct sum. Then there exists some element such that this is equal to 1 R1, 1 R2, 1 Rn. Okay, and because the ring is commutative, we are not writing the other product obtained by interchanging these two. Thus, AIBI is equal to 1 Ri. Okay, so that means we have Bi in Ri because we are choosing this n tuple from this direct product. Bi belongs to the ring Ri such that AIBI is equal to the unity in Ri. So this tells us that the element Ai belongs to the group of units of the ring Ri. Hence, AI belongs to URI for all I, which implies that this belongs to the direct sum of these groups. Okay. And that in turn implies that U of this is contained in this as a subset. That we are not writing. Okay, this is understood. Next, let any element in the direct sum of the groups. I need some ink. Then Ci belongs to URI for all these i's. Thus, for each I, Ti belonging to Ri such that Ci equal to 1 Ri, because Ci is a unit, that is, it has a multiplicative inverse. Let such an inverse be Di. Then this n-tuple belongs to the direct sum of the rings such that so this equation tells us that this has a multiplicative inverse in this direct sum, and that inverse is this. In other words, this is a unit in this ring. And keep in mind that we are not writing the other product because everything is commutative. Hence, so any element in this direct sum of the groups of units is also an element in the group of units of the direct sum of the rings. This shows that these two groups are equal. that completes the solution. Then determine the group of units of the ring of polynomials with integer coefficients. Okay, so that means we have to determine those polynomials that have multiplicative inverses in that ring Zx. So let us consider one polynomial such that there exists Gx again belonging to that ring for which fx times gx is equal to the unit element in that ring, the unity in that ring, which is the integer 1. Now look at this equation. In this equation, the left hand side is a product of two polynomials, but the right hand side is a constant. Now because this constant is non-zero and product of two integer polynomials is 0 if and only if one of them is, at least one of them is 0. So none of these two polynomials can be 0. That means they have degrees. Since are both non-zero, degree of f of x plus degree of g of x is equal to, we know this property of polynomial rings, degree of f of x times g of x. Keep in mind that this is possible because this z or z, the ring of integers, is an integral domain. Otherwise it's not necessarily true. For example, say you consider these two polynomials. Say okay, say in this polynomial ring you consider these two polynomials 3x cubed plus 2 and 2x plus 1. Okay, now the first polynomial has degree 3, the second polynomial has degree 1. But if we take their product, what do we get? If we first just simply perform the multiplication, we get 6x to the power 5, oh sorry, it's not x to the power 5, x to the power 4 plus 3x cubed plus 4x plus 2. Okay, but we are in the ring Z6, so where 6 is equal to 0, so this polynomial actually is 3x cubed plus 4x plus 2. So the product also has degree 3 and not 4. Okay, and this has been made possible by the fact that Z6 is not an integral domain. It has the 0 divisors 2 and 3, and in fact we have used 2 and 3 to create this example. So integral domain is needed for this degree equation, this formula to be true. Okay, so now this is not a part of the solution, so let's just wipe it out. Now this is equal to degree of 1 is a constant, so its degree is 0. Now degree by definition is a non-negative integer, so sum of two non-negative integers is 0, so each one has to be 0. Thus that is f of x and g of x are constant polynomials. Constant polynomials in this ring means they are integers. So the equation now we can say something more from this equation, because now we know that they are not just any integer polynomials but actually integers. So this equation implies that f of x is either +1 or -1. Hence, in spite of having an infinite ring, this ring of integer polynomials, the group of its units has only two elements, the integers -1 and 1. The next one is also similar, but here in place of integer polynomials we have real polynomials. And since we have seen the strategy here, I'm not going to write those things again because things will be exactly similar. Proceeding like the previous solution. One can show that, okay, you see here also if you go like this you will end up with an equation like this, and in place of this you will have this. that these are again constant polynomials, but now they are real numbers. So product of these two is equal to 1. That means this is a real number which has a multiplicative inverse. That means it has to be a non-zero real number. So in this case, the group of units is the group of all non-zero real numbers under multiplication. Proceeding similarly. Do you notice one thing, that here the group of units turns out to be equal to the group of units of this ring. In this case, the group of units turns out to be the group of units of the ring R. Then 27. The fact that I have written a solution like this does not mean that you should write just this much. You please do it like this. Okay, one can show means you show it for yourself. Now exercise 27 says, but show that a unit in a ring divides every element. Let her be a division, or rather divisibility, has it been defined for arbitrary rings or commutative rings? So far I remember the notion of divisibility is defined only for commutative rings. So I am going to assume commutativity, okay, although that is not explicitly mentioned here. But if I see something, if I see that it has been defined in the text for non-commutative rings also, I will come back to this exercise in the next video. Okay, let us do it for commutative rings. A commutative ring, since we are talking about units, so we need a unity in this ring, otherwise units don't make sense. Let R be a commutative ring with unity 1. Since we don't have any other ring, so we don't need to add some suffix. Okay, we can just say that the unity is 1. Let A be a unit, that means A belongs to the group of units and B be any element in R. We need to show that A divides B. Then there exists C belonging to R such that AC is equal to 1, because A is a unit, so it will have a multiplicative inverse C. Now B is equal to B1, B can be written as B1, but 1 can be written as AC, which, considering the fact that multiplication is associative and now also commutative, this product can be written as BC times A. So we have shown that B is something times A, and that something definitely belongs to the ring again, and combine that with the fact that A is non-zero. A is non-zero because had A been 0, the left hand side of this equation would have been 0, giving us 0 equal to 1, which is not allowed for the type of rings we are considering. 0 is never equal to 1. So A is non-zero. Non-zero. This shows that A divides B. So any unit divides any element of the ring. So that completes the solution. Then 28. In C6, show that it's somewhat difficult to remember which notations are used in which books. It's easy to get confused between Herstein's topics in algebra and Gallian's algebra. So this notation is there, so we don't need to write A divides B, we can just simply write like this. Show that 4 divides 2 in C8. Show that 3 divides 7, and in C15 show that 9 divides 12. So in each of these 3 cases we just have to show that the second element is the first element times something from the ring. In Z6, 4 times 2 is equal to 2. 4 times 2 ordinary, if you consider ordinary multiplication, then this is 8, but modulo 6, that is 2. So that's why 4 divides 2, which is not true in the ordinary ring of integers. In C8, 3 times 5 is equal to 7, because 8 plus 7 is 15. No, wait, what? In Z8, okay, oh, I think I have mixed things up. In Z8, this equation does not make sense, does it? 15. So because 8 plus 7 is 15, so this is correct, no? Oh, because the next one is Z15, I was thinking I made a mistake. No, it's okay. So that's why 3 divides 7, which is not possible in the ordinary ring of integers, because 3 and 7 are distinct primes there. And in C15, 12 is equal to 9 times 3. So that's just it. Let us do one more. For this one, the answer is given in the text itself. Suppose that A and B belong to a commutative ring R with unity. If A is a unit in R, and B is an element whose square is 0, show that A plus B is a unit of R. And in this case, the multiplicative inverse of A plus B turns out to be this. Note that A inverse. Oh, okay, see, I forgot that this the notation for the inverse is also available to us. A inverse denotes the multiplicative inverse of A when that exists, and it's given that A is a unit, so A has a multiplicative inverse. So that means we can consider this element. Such that if we take this product, what do we get? Using all the ring axioms and elementary properties, distributive law and everything, we get A inverse minus, let us first write all the terms and then we will simplify each term, plus BA inverse minus BA inverse whole square times B. this is 1. 1 is of course the unity in the ring, minus 1 A inverse, and A gives us 1. That vanishes and we are left with 1 A inverse. B A inverse can be written as A inverse B because the ring is commutative. And here we can write the last term like this, again because the ring is commutative. These two things give us 0, 1 minus. Now since b square is given to be 0, so ultimately we get 1. So that's why this acts as a multiplicative inverse of a plus b. Is a unit of R. So let us end the video here itself. In the next one we will complete this set of exercises. We will try to complete. So that will be all for tonight. Today is 15, 16, 17, 18. So on 18 we will have our usual real analysis video. So see you then. This is me, Lucifer, from a mathematical room. If you have anything to say regarding these things, you can write in the comment section below. Have a nice night.